Hello and welcome! In this lesson, we will learn how to generate a boundary layer mesh using the Add Boundary Layers task in the Ansys Fluent Meshing Watertight geometry workflow. We will begin with discussing the importance of boundary layer mesh in fluid dynamics, followed by a discussion on the methods available for adding boundary layer mesh along with the user inputs required. Without any further ado, let's get started. We are well aware of the concept of boundary layers in fluid dynamics and their influence on the overall fluid flow. These thin viscosity-dominant regions that form along the surface of a solid body as a fluid flows past it play a significant role in defining skin friction drag, heat transfer, aircraft wing stall, etc. Hence, it is critical to ensure that CFD simulations properly model the physics of the fluid flow in these regions. In addition to using appropriate numerical schemes, it is necessary to ensure that the mesh in these regions is fine enough to adequately capture fluid flow behavior. For this purpose, the Watertight workflow in Ansys Fluent Meshing has a dedicated task, that is, the Add Boundary Layers, which can be used to define the meshing requirement in the boundary layer zone. Let us now take a look at how to use this task using an example. Launch Ansys Fluent in meshing mode. Go to File, Read and select Mesh, and then pick the provided mesh file. Once Fluent finishes reading the file, you will notice that the Watertight geometry workflow has been automatically set up and all the tasks till the Update Regions task have already been successfully completed. The model we have here is that of a generic ball or check valve, which consists of one solid region, that is the pipe geometry, and three fluid regions, that is the inlet pipe region, the valve region, and the outlet pipe region. The ball valve is considered as a void in the model. Let us now look at the Add Boundary Layers task. If the Add Boundary Layers setting is set to Yes, multiple input options are populated below this setting. The Name field can be used to specify a name to the applied control settings. By default, the name is auto-populated based on the offset method type that is chosen. There are 4 different offset method types available for adding boundary layer mesh. Each of these methods have their own set of user inputs. The inputs common to all the methods are the number of layers, add in, and grow on. As the name suggests, the number of layers input defines the number of boundary layers that the user wants to create, and this number strongly depends on the accuracy requirement needed for resolving the boundary layer flow. Add in and grow on inputs define the locations of boundary layer mesh generation. The add in option specifies the region or a volumetric zone of the CFD model in which you would like to add the boundary layers. Once the region has been selected, the Grow On option is used to specify the surfaces on which boundary layers need to be added within that region. By default, Add In is set to fluid regions and Grow On is set to only walls. However, boundary layers can also be added in the solid regions or any other specified regions as required by making appropriate selections under the add-in user input, and can also be added to interfaces or other specified boundary zones or labels by making appropriate selections under the Grow On user input. Additionally, there are 2 advanced options which can be left to their default for most of the cases. For further details, please refer to the user's guide. Let us now look at the offset method type. The default option is Smooth Transition. It is the most robust and useful for most of the applications. This method requires transition ratio and growth rate parameters as additional inputs. Transition ratio is the ratio between the height of mesh in the last boundary layer and the first cell in the volume fill, whereas growth rate is simply the ratio of thickness of the next boundary layer cell to the previous boundary layer cell as viewed away from the surface on which the layers are being grown. Keeping all the settings to default, generate the volume mesh. As shown here, the boundary layer mesh thickness and the first layer height vary along the surface depending on the local surface mesh size to establish a smooth rate of volume change between the boundary layer mesh and the volume mesh, which is a major advantage of this method. However, on the downside, it is not possible to directly control the first layer height or the absolute total height of the boundary layer mesh. The next method we will look at is the last ratio. Here, the first height, which is nothing but the thickness of the first layer of the boundary layer mesh, is given as an additional input and is maintained wherever the boundary layer mesh is created. Relative to the smooth transition method, one can notice how the first layer thickness is constant everywhere. Additionally, by defining the transition ratio, a smooth transition is ensured between the boundary layer mesh and the volume mesh. The only downside to this method is that the growth rate between the layers is automatically varied to satisfy other inputs. As a result, the boundary layer thickness varies along the surface. Let us now look at the next method, that is the uniform method. This method depends on the growth rate and the first height as additional inputs to generate the boundary layer mesh such that the thickness of each layer remains the same anywhere in the domain. For flat surfaces or relatively lightly curved surfaces, a uniform thickness can be easily maintained. However, at sharp corners, such as 90-degree bends as shown here, this method can lead to the creation of crevices. A severe limitation of this method is that the volume change between the boundary layer mesh and the volume mesh cannot be directly controlled. The last method we will look at is the aspect ratio method. Here, the first aspect ratio and growth rate are required as additional inputs to define the boundary layer mesh. The first aspect ratio is the ratio of the local surface mesh size to the height of the first cell of the boundary layer mesh. As the surface mesh size changes around the model, the first cell height is subsequently modified to maintain the user-defined aspect ratio as shown here. The major drawback of this method is the lack of control on the first layer height and the total height of the boundary layer mesh. Let's summarize. In this lesson, we learned how to generate a boundary layer mesh using the Add Boundary Layers task. We discussed the importance of boundary layer mesh and explored the nuances of the methods available for adding boundary layer mesh along with the user inputs required. That brings us to the end of this lesson.